This is the third video of the 3-video series on file systems. In this video, we will talk about examples of how a real file system works. In this video, we discuss the file allocation table, also known as the FAT file system. We will also discuss a multi-index based structure known as the inode that was first introduced by Unix. So, what factors are critical to the design choices of a file system? Well, durability is of prime importance in long-term memory storage. Disk performance, basically to maximize sequential access and minimize the seeks. We also need to be able to open first and then do reads or writes. Because on open, we actually first check that the file exists, and secondly, that the user has permission to use the file in the way you want. So, basic entities on disk are files and directories. Files are a user visible group of blocks arranged sequentially in the logical space. Usually, directory is a hierarchical structure, which is a collection of files with information in them. We also need to allocate and free blocks such that access remains efficient. Okay, and we need a way to track the disk blocks so we could link all the blocks together, but that might be slow. So we can use bitmap to represent free space on disk by using best fit or first fit algorithms. Then ultimately, we need a way to structure files. As we know that files are a bunch of blocks, not just one block. So we need to track which blocks belong to which offset within the logical structure, and we call this a file header. And we need to optimize the placement of files on disk blocks to match access and user patterns. Following are some of the components. So here we start with a file path that gives us something to look up in our directory structure, which is actually going to give us what we are going to call a file name, which is really just an index into a file header structure, which will then find us the file header of the inode that we will be describing soon. The index of the file will tell us which disk blocks are part of the file. So this is a very simple diagram, right? That is all we need to know to identify what's a file system and what's the difference between various file systems, which is how these blocks are structured, right? An open function performs an actual form of name resolution, which basically translates a path name into a file number, which is going to be our index to locate blocks, okay? And it's going to create a file descriptor in the process control block in the kernel. Then it will return a handle to the file. And then we can use this handle to read, write, seek, and sync operations. The user simply see files and directories. And the file management system actually maps the logical blocks of the user data into sectors on a disk drive. The file management system is one of a major activity that the operating system should be able to perform in a way that abstracts away the complexity of the hardware and provide the user in a way to manage their data. We have studied various allocation methods in the previous video. These mappings are what defines a file system, such as FAT16, FAT32, NTFS, and ext3 file systems. All of these file systems actually provide an interface to the user which with various support and allows the user to perform various activities on their files, such as creating a file, reading, writing, deleting, modifying, truncating, etc. So every time a file is created, it contains the data that are blocks on disk somewhere, and the file system also creates certain attributes of the file. These are the metadata of your file. And what are metadata? Metadata are data about the data. So what does that mean? Actually, when you create a file, you obviously need some name to identify the file on the disk drive, which is a unique number given to a file, because for the operating system, everything is a file. Other attributes include the ownership of the file, size of the file, when was the file last modified or last accessed, then the protection and permissions to know the access level given to various users. And some file systems also provides you with encryption and compression options. So all these attributes are provided by the file system. And by the way, this is the reason why sometimes we feel that our disks have not been utilized completely, because some space are required for tracking metadata information of the files, without which we would not have been able to access our data. Although it occupies very less space on the disk, nevertheless, the space is very important for file management. Now we move on to start looking at an example of a file system known as the FAT file system. The FAT file system was originally developed in 1977 for use on floppy drives. However, it was soon adopted by MS-DOS and Windows 9X for 2 decades, and still can be found for reasons that we will see. So firstly, assuming that somehow we have a way to translate a path to a file number, and also keeping in mind that data disk storage is basically just a collection of blocks laid out in a way that is accessed efficiently, right? Here we have 3 blocks that might be some file on the disk, okay? And the question is, how do we link these pieces of data together into a file? Because if you notice, the data is not placed contiguously, rather it is placed randomly here and there. Note that we have numbered the blocks from 0 to n minus 1. And so these blocks are scattered, they are not sequential. So how do I associate them together? And that is the sort of question that the file system is supposed to answer, right? Associating blocks of files efficiently so that they are stored, retrieved efficiently, okay? And why is the data laid inside the disk in this manner? Well, this has a lot to do with the scheduling policy of the disk drive. There can be many reasons for this fragmentation, but we needed such an example to better understand the process of how the FAT file system works. And how does it links these blocks of data. Now, for instance, suppose that we are interested in reading file number 31, block 2, offset X. And how do we do that? Well, we index into the file allocation table with the file number 31. So this file number basically is position 31 in the FAT table. And that is what I got back from my directory, okay? So when we looked up this data in our directory, it gave us back 31, okay? And that is the first block of the file. And then once we follow the links, and then we can read the data of the disk into the memory, okay? So basically, all the file allocation table does is it is a set of linked lists that links together either files or free blocks, okay? We will talk about free blocks shortly. So basically, FAT entry number 31 links to 32, which then links to whatever this is over here. And that's how we find all the blocks of the disk. And that is the responsibility of the file system. And that is basically to do this level of organization and to maintain the FAT table based on your data and write patterns, okay? File numbers are really only the valid starting positions of files. So 32 in this instance isn't actually a file number, it's a block number, okay? So the only file number that are valid are ones that are actually in directories that you can get by a directory search, okay? Now let's look at some properties of the FAT file system. Files are a collection of disk blocks. The FAT file system links these blocks in a single linked list, right? The file number is the index of just the root of each file. We follow the linked list to get the block we want. The unused blocks are in a free list. So for instance, we have a free pointer that basically links all the free blocks or free spaces. Okay. So what about the write operation? So let's actually see that working. Uh, when we want to write block 3 to this file, file 31. So how does the fat file system manages this and writes block 3 to the file? Well, first of all, there is no block 3. So we have to take a block from the free list, readjust the linked list to point to that to the block 3. So that block 3 now points to null or end of file, right? And then we can do a write. Okay, I hope that was easy. Let's create a brand new file to see how the fat file system handle that. So what does the fat file system actually do? First of all, it frees a block and creates a new file number, which we are going to put in some directory. Somewhere in the free list, we write the first block and we allocate the second block by linking it to the first one, and so on and so forth. Where is the fat basically stored? Well, it is stored on disk and in a well-defined place at the beginning of the disk. And when the system is switched on, a copy of it goes to the main memory because you want to perform linear search in RAM. So what happens when you format a disk? You basically reset all the blocks and link up the fat as a free list. Okay. So here are some natural questions that comes to mind while evaluating any file system. How long does it takes to find a large file? Well, it takes a long time because you have to walk through the fat table. So this is basically bad for random access. And even worse if you did not cache the fat in the main memory. The free list is just a bit vector. In the fat file system, it's a linked list. So that's a problem. We might be able to use some sort of next fit algorithm to try to do locality in this. But oftentimes, it does not happen. The fat file system isn't good at laying the data out. So it does not take into account the locality of data. So one of the design specifications of a good fat system would include the requirement that the data blocks laid out sequentially. Is the sequential access good? Well, that is not bad. However, the random access is bad. Does it handle fragmentation? No. You have a lot of fragmentation, as can be seen in the example we have on the screen. How does it handles small files? Well, the files that are smaller than the block size, you simply are wasting things, right? You are wasting the sector of the disk. Also called internal fragmentation. So this is called internal fragmentation. How does it handle big files? Well, as far as FAT is concerned, it can handle big files. But then the walkthrough, the linked list has their limitations because the main operation that is intensively invoked is the linear search module, and you need that module for almost all types of activities that the FAT system allows you to perform, such as when you create a file, you modify a file, you read some blocks from a file, you delete a file. You need to walk through the linked list, which is not that appealing. There is a lot of security holes in FAT. Okay, FAT has no access rights. There is no header in the file block. So the file number is actually a block number, as we have seen in this example, right? So note that basically there are lots of limitations, and most of the people who care about storing their data in a more reliable and efficient way don't use the FAT file system. FAT systems are usually used for little plug-in drives or small-scale standalone systems. We have talked about files, but what about directories? If you think about a real fat file system with much larger file numbers, /home/some folders, so this directory is actually just a file. and you start searching through the file linearly until you find, let's say, uh, work or desired directory slash home slash some folder slash work, which is assigned the file number 8028.374. So the directory is basically a hierarchical structure uh, that performs name resolution, that maps the name into a file number. Okay, so the header basically consists of a name and file number, as well as a pointer to the next file. Essentially, directories are basically files that are mapping of file names and file numbers. Then we have the free space, okay, for new entries or where files have been deleted. In the fat file system, the attributes are kept in directories, and each directory is a linked list of entries. So, where is the root directory? In the fat file system, it's basically the first file on system. Okay. So usually there's a bunch of resolutions. This is called name resolution, where we check the file header and search for the entries of the path, for example, slash home, slash some folder. Okay. As can be seen that we simply search through a hierarchy of directories before finding the required file. There are a bunch of resolution. This is called name resolution, where we check the file header and search for entries of the path. For example, slash home slash some folder slash sys.txt. So you can imagine how many disk accesses are involved here. Then there are two kinds of accesses. One, um, when you have to specify the whole path, this is absolute path, uh, slash home slash some folder slash sys.txt. But it is not convenient to work with an absolute path, right? Especially if you are working with deeply nested directories. There is another scheme which makes this look easier through what is usually called the current working directory. So relative paths instead uses a location relative to the current working directory, because now you would only refer to a file by just its name. So let's look at this form from an example directory. We have a directory whose structure is as follows. The topmost directory in the file is the root directory, that is denoted by a slash. And here is our directory structure. Okay. So the absolute path would represent a complete path to the file, which looks something like this. So the command prompt basically would look for the specified name within the directory, right? So assuming that the current working directory is the work directory, so the command prompt for the relative path basically would look for the specified file name within the current directory. For example, if the current working directory is work, then the relative path for the MCS folder would just be MCS, rather than having the full path from the root. We can just have the path from the working directory. You could also write relative paths for files and other directories. For example, the relative path for the sys.txt file relative to the work directory is just MCS slash sys.txt. Notice that unlike a full path, the relative path does not start with a slash. That's how you can tell a relative path from an absolute one. You can also write relative paths for items that are closer to the root. The special directory entry dot dot takes you from a directory to its parent directory. So if you are if you are in slash home slash work slash bscs, and you refer to dot dot, you're talking about the directory /home/work. Uh, and if you refer to dot dot slash bscs, you are referring to /home/work uh, bscs. There's a lot of there's also a special entry which is just dot. uh, Dot basically points from each directory to itself, and here the dot refers to /home/work. So now let's move on to the inode file header. So what is the inode structure? The inode structure is actually the indexed file structure that started out in BSD 4.1 and is used in a lot of systems these days. So what is an inode? Well, unlike the index-based allocation method, there was a single index blocks, which limits the file size it can represent. The inode has multiple levels of indexing that supports both small and large files. Unlike the FAT file system, the file number here is an index into an inode, which provides enough information that describes the complete structure of the file. The inode structure describes all the attributes of the file, plus you have pointers to a bunch of blocks. Okay, which user owns the file, what group is part of this file, when then it has the 9 access rights uh, given to the user group and owner group, such as uh, the read, write, and execute. The set user ID and the set group ID are Unix access rights flags that allow users to run an executable in a very controlled way. If you look further into the inode structure, there's a bunch of direct pointers that points to 4 kilobyte of hits blocks, and there's 12 of these direct blocks, and that's what makes a file size of up to 48 kilobytes. And then to address large files, we have up to 3 levels of indirect pointers called indirect blocks for representing up to uh, 4 megabyte of file size. The doubly indirect level addresses up to 4 gigabytes, and triply indirect pointers can represent up to 4 TB. That is all about the file systems. And in the end, I encourage you all to have a look at the NTFS structure, and also to have a look into the code and libraries that implement these file systems. I hope these series of videos were helpful. Thank you.